Welcome friends, Igor is here, and in this video we will understand why it is useful to know the determinant of a matrix. In this lesson we will compute the determinants of all elementary matrices and all singular matrices. We will establish that a square matrix is non-singular if and only if its determinant is not equal to 0. And we will prove that the determinant respects matrix multiplication. Let's get started. First simple observation is that the determinant of the identity matrix is equal to 1. That is because the identity matrix is in upper triangular form, and we already discussed that the determinant of a matrix in upper triangular form is equal to the product of its entries on the main diagonal. This allows us to compute the determinants of all elementary matrices. If an elementary matrix was obtained by swapping two rows of the identity matrix, its determinant is -1. If an elementary matrix was obtained by multiplying one row of the identity matrix by scalar alpha, then its determinant is equal to alpha. And if an elementary matrix was obtained by multiplying one row of the identity matrix by scalar alpha and adding the result to another row, then the determinant of this matrix is equal to 1. This result is a trivial consequence of our earlier observations on how performing elementary row operations affects the determinant. For example, if we swapped two rows of the identity matrix to get an elementary matrix, then we have changed the sign of the determinant of the identity matrix, but the determinant of the identity matrix is 1. Therefore, the determinant of the corresponding elementary matrix is -1. But the most important piece of information for us from this result is that the determinant of each elementary matrix is not equal to 0. Remember, in the second type of an elementary matrix, alpha has to be a non-zero scalar. And now let's prove that if you take a square matrix A and multiply on the left by an elementary matrix E, then the determinant of the matrix product is equal to the product of the individual determinants. We will show why it holds for each type of an elementary matrix. First, suppose that we deal with an elementary matrix which was obtained by swapping rows I and j of the identity matrix. Let's also construct a matrix B by performing this same row operation on the matrix A. In the previous video, we discovered that this matrix B can also be obtained by multiplying matrix A on the left by this elementary matrix. So, the determinant of the elementary matrix times matrix A is equal to the determinant of the matrix B. On the other hand, the matrix B was obtained by swapping two rows of a matrix A, therefore, determinant of matrix B is negative determinant of the matrix A. The last step is to recall that the determinant of the elementary matrix obtained by swapping two rows is -1. Second, let's look at an elementary matrix which was obtained by multiplying row I of the identity matrix by scalar alpha. Let's perform this same row operation on the matrix A, and the result is the matrix B. Same idea as in the first part. The matrix B can be expressed as a product of the elementary matrix and the matrix A. On the other hand, matrix B was obtained from A by scaling one row by alpha. Therefore, the determinant of B is equal to determinant of A multiplied by alpha. The last piece of the puzzle is to recall that the determinant of an elementary matrix of the second type is exactly alpha. Third, let's say we have an elementary matrix which was obtained by multiplying row I of the identity matrix by alpha and adding the result to row j. Let's also apply this same row operation to matrix A to produce matrix B. Then this matrix B is the product of the elementary matrix and matrix A. On the other hand, because the matrix B was obtained by applying the row replacement operation on matrix A, they have the same determinant. The last observation is to recall that the determinant of an elementary matrix of type 3 is equal to 1. And now we are ready to prove that a square matrix is singular if and only if its determinant is equal to 0. This is an if and only if statement, and therefore we need to prove two implications. But before we get to that part, let's make some observations. We have a square matrix A, and let B be the reduced row echelon form of this matrix A. This means there is a sequence of elementary row operations that transforms A into B. But then by reversing this sequence of row operations, we can also transform matrix B into the matrix A. So, for this sequence of row operations, which transforms the reduced row echelon form B into the matrix A, we will record the sequence of corresponding elementary matrices. And then, performing this sequence of row operations on the matrix B is equivalent to multiplying this matrix on the left by the corresponding sequence of elementary matrices. The result of this is the matrix A. Now, let's compute the determinant of A. It is equal to the determinant of this long product of matrices, and let's think of this long product as follows. It is the leftmost matrix ES multiplied by the rest of the product. By the last theorem we just proved, this is equal to the determinant of the matrix ES multiplied by the determinant of the other matrix. But then we keep doing this. We chip away one leftmost elementary matrix at a time. We keep applying this same theorem, and this is what we'll get in the end. So, the determinant of A is equal to the product of all these determinants. But let's recall that the determinant of each elementary matrix is not equal to 0. This means that determinant of the matrix A is equal to 0 if and only if the determinant of the matrix B is equal to 0. That is because in this product on the right-hand side of this equation, all determinants of elementary matrices are not equal to 0. So this is our key observation. Let's keep this in mind. The determinant of a square matrix A is equal to 0 if and only if the determinant of its reduced row echelon form B is equal to 0. We are not saying they have the same determinant. This is simply not true. But we are saying that there are 0 at the same time. Now we are ready to prove the two implications in the theorem. First, we are going to assume that the matrix A is singular, and we would like to prove that its determinant must be equal to 0. If the matrix A is singular, then its reduced row echelon form is not the identity matrix. But B is a square matrix which is in reduced row echelon form, yet it is not the identity matrix. It means that matrix B must contain at least one 0 row. But in one of the previous videos, we already proved that a matrix with a 0 row must have 0 determinant. So, determinant of B is equal to 0. This means determinant of A must also be equal to 0. In the opposite direction, let's assume determinant of A is equal to 0. We need to prove that then A must be a singular matrix. This is going to be proved by contradiction. Let's assume that A is actually non-singular. Then its reduced row echelon form B is the identity matrix. And the determinant of the identity matrix is equal to 1. In other words, it is not equal to 0. But if determinant of B is not equal to 0, then determinant of A cannot be equal to 0. This is a contradiction to our assumption that determinant of A is 0. This contradiction was caused by us assuming that A is non-singular, therefore this is impossible, and hence A must be a singular matrix. Because this was an if and only if condition, we can also say that a square matrix is non-singular if and only if its determinant is not equal to 0. Our last result is a remarkable observation that determinant respects matrix multiplication. The determinant of the product of two matrices A and B is the product of their determinants. Notice in this equation, on the left-hand side, it's the operation of matrix product. On the right-hand side, it's the operation of the product of numbers. This proof is going to be proof by cases. In the first case, we are going to assume that the matrix A is singular. Then, its determinant must be equal to 0. Also, in one of the previous videos, we have proved that a product of matrices is a non-singular matrix if and only if all individual matrices are non-singular. This means the product A times B is a singular matrix because at least one of the terms, A, is a singular matrix. But being a singular matrix, the matrix AB must have 0 determinant. And now we see that the formula holds in this case, because determinant of AB is equal to 0, which can be expressed as 0 times determinant of B regardless of what determinant of B is, and we also know that 0 is equal to determinant of A. The second complementary case is when the matrix A is non-singular. Then A can be expressed as a product of elementary matrices. So to compute determinant of the matrix product AB, we are going to replace the matrix A by the corresponding product of elementary matrices. We are going to chip out one elementary matrix at a time from the left, and we will arrive to this product of determinants. Now comes a creative trick. Let's reverse this process of chipping out one elementary matrix at a time on the left backwards, but let's now exclude the matrix B from the consideration. This gives us exactly what we're looking for. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will introduce eigenvalues and eigenvectors of a matrix. I will see you later.